Hello and welcome back to the Illumination Talks by myself, Ralph Ellis. The talk today is coming from my Megalithomania talk, which I did back in early May. And when that comes out on Megalithomania, I do recommend you go and have a look at their site because they'll have nearly a dozen speakers, I suppose, over the 2 days of the conference. And this is the talk that I gave at that conference, and it's about the dating of the megalithic era. So without further ado, here it is. This is my Megalithomania talk. So welcome to my talk today, which is on dating the megaliths by myself, Ralph Ellis. And this is an interesting talk because how do we know how old the megaliths are? You've probably seen lots of perhaps carbon-14 dating, but you have to be careful with carbon-14 dating because you don't necessarily know if the artifact that you're dating is actually related to the construction era of the megalith. It might have been placed there after 1,000 years or 5,000 years. It might be much later than the construction period for your megalith. So how do we know how old the megaliths are and how can we date them? Well, let's have a look. This is all taken from my two books, Thoth, Architect of the Universe and K2, Quest of the Gods. The Megalithic Maps trilogy, I call it, a trilogy in 2 parts. These books are nearly 25 years old now, so this is going back quite a long way in my research, but the data in those books is still relevant and good, and this talk is taken from those 2 books. So how can we date the pyramids? Well, one method is through erosion. You might have heard the controversies over erosion of the Sphinx enclosure over at Giza, where it has been said that the erosion patterns on the Sphinx enclosure are much greater than you would expect for something that was just 4,500 years old. That may well be true, but the trouble is with that erosion pattern you have nothing really to compare it with. So really you need a control that is, say, 1,000 or 2,000 years old with a set erosion pattern, and then you can compare the two. But there is no other pattern to compare the Sphinx enclosure with, so it can only give you a guesstimate at best. Here's another erosion pattern. This is down at Dashur, the bent pyramid, and here on the left we see less erosion because this area was always covered up by the mortuary temple, and so it was protected and it didn't erode. And on the right side we see more erosion. This is how much erosion you get from the very time this pyramid was built. This is how much erosion you get. Not so much as you see, but this was made of very hard and durable Tura limestone, which weathers very well, and so we don't see a great deal of erosion. How long ago does this represent? Well, we don't know because we have nothing to compare it against, and that's what we want to have a look at later in this talk. Here is some more erosion. So this is down at the step pyramid at Medum, and here we see much more erosion. So down at the bottom here we see less erosion because this was covered up first by the debris that's here on the right side. Why the debris? Well, this particular pyramid was made of a very poor stone, which was used as the casing blocks, and it has eroded very, very rapidly in comparison with Tura limestone. And this material has dropped down the bottom and it has protected the area at the bottom here. Now, it was said at one point that this pyramid collapsed in a sort of big avalanche, but it didn't, because when they did this excavation, this material on the this debris here on the right hand side is stratified, and so it must have come down slowly over the decades, over the centuries, over the millennia, building up this big pile of debris here. And as the debris pile climbed up, it protected more and more of the casing blocks. And so at the top here, this area was exposed for much longer, of course, because it wasn't covered up so quickly, and we get more erosion. And at the top here, we see almost complete erosion. That's interesting, because here at the top we get 3 or 4 meters of erosion. The entire casing block has weathered away. And you have to ask yourself, even if this casing block is rather friable, it's not very durable, how long does it take to weather away a complete side of a pyramid? A very long time indeed, I would say. The core of the pyramid here is still intact because it's made of a much harder stone. So all this is telling us is again that the pyramids might be very, very old, but we can't really get a date because we have nothing to compare this erosion with. Another method of dating the pyramids might be... Oh, and before we leave that, what this means is that Medum was abandoned because nobody was looking after this site, no one was clearing away this debris, nobody was repairing the casing blocks. It was simply eroding over millennia. So how else can we date pyramids? Well, here's some other erosion patterns. This is back at Giza. This is the platform upon which the Great Pyramid was built. So before they built the pyramid, they built this wonderful level platform of Tura limestone, very hard Tura limestone. And that was eroding here on the left side ever since the pyramid was built. And this is one block of stone, remember, this is not 2 blocks of stone. So let's have another look at, because this is all around this pyramid, all around the base. So let's look at another section of this. And here again we see this differential. And we like differentials because they may give us a date. So why do we see this differential? Because on the right side here, this was always covered by by casing blocks. So that was the original edge of the pyramid itself. And those casing blocks were protecting this paving block on the right side. But on the left here, this was eroding ever since the pyramid was built, many thousand years ago. But then someone came along about 1,000 years ago during the Muslim era, and they stole all of the casing blocks. And now the pyramid, the paving stone can be eroding on both sides, both on this newly exposed side and this always exposed side. And the interesting thing is that there is this large differential, and there is at least 10 times more erosion on the left side than on the right side, which was protected. But the thing is, we know when this side started eroding, the blue side, the right side, we know when that started eroding. That was about 1,000 years ago. And if there's 10 times more erosion on the left, then we could say the Great Pyramid must be at least 10,000 years old. Much older than is classically given for the date for the Great Pyramid. So at least 10,000 years old, based on the amount of erosion of the pavement upon which it is sitting. How else can we tell how old these pyramids are? Another way might be through repairs. Here we're back at the Bent Pyramid down at Dashur, and someone has been repairing this pyramid. And if you look across the side of this pyramid, you will see repairs all over this pyramid. So at some point in the past, Pharaoh has covered the entire pyramid with scaffolding, sent his artisans across this pyramid, chipping out all of the eroded blocks and the cracked blocks and putting in these repair blocks. The thing is, we don't know when this was done. All we have is an association between this pyramid and a particular pharaoh whose name was Snefru or Snorfru, and it is claimed that because he's associated with this pyramid, that he built it, and that he built the Red Pyramid and the Step Pyramid as well. So Snefru is associated with 3 pyramids. And he lived 4,500 years ago, and we have no record of any repairs being done to these pyramids since the time of Snefru. But of course there is no evidence that Snefru built this pyramid. There are no inscriptions inside the pyramid, in the burial chambers. There's nothing to connect this pyramid with Snefru inside this pyramid. So what if we were to say perhaps that Snefru was associated with this pyramid not because he built it, but because he repaired it? In which case we could say that the pyramid was built at least 4,500 years before the time of Snefru, maybe up to 9,000 years, double that amount of time. So from its time of construction, it lasted for 9,000 years before it needed repairing. And then Snefru repaired it 4,500 years ago, and those repairs still look mostly okay even today. If that is the case, then this pyramid was built some 13,500 years ago. Again, much earlier than is classically given for these megalithic pyramids. But how could we confirm this? One other method might be astronomy or astrology. If your particular megalith was built orientated towards some sort of cosmic event, you know, a midsummer sunrise or a particular constellation or a particular star, well, those stars have movements because of the movement of the Earth, and therefore we might be able to get some sort of date from these movements. And the first movement we're going to look at is axial precession, the precession of the Earth. And as you probably know, we've talked about this many times before, a gyroscope will precess. So let's have a look at that. Here is a gyroscope precessing. It wobbles on its axis, and that's perfectly normal. And the Earth is just a very big gyroscope. So what are we looking at here? Here's the Earth. Here is the celestial axis, the axis of the Earth as it spins. And currently it's pointing at Polaris. But it wasn't always pointing at Polaris. It moves, and it moves around the north ecliptic pole. This is the red spot you see here. So let's have a look at that movement. And it draws this big yellow circle in the heavens above, known as the ecliptic circle. So the celestial pole moves around the ecliptic pole in this big precessional circle. And it's quite possible that we can use these movements to date some of our megaliths. So where do we get this information from? We get it from Monsieur Lascar, who was based in Paris, still based in Paris, I believe. And he is the the authority on the movements of the solar system. Everybody comes to LASCAR information for the movements of the planets and the Earth. And so we can download that precession data. LASCAR has calculated the precession of the Earth back 20 million years. So quite a long time ago. It's a very stable movement that is very predictable. And you can download that data and you can draw a nice little graph. So here's the graph. What are we looking at? Well, down the bottom here we have dates. We have 0 here, today's date, and we go back 100,000 years here. On the left side we have degrees. Obviously the precessional movement makes a circle in the heavens, a circle of 360 degrees, and it forms this nice sawtooth pattern. And here we're using Leo as the prime meridian, and so Leo is down here at 0 degrees, or up here as well at 360 degrees if you really want. Anyway, we're using Leo as the prime meridian. And we have this wonderful, predictable movement of the axis of the Earth. And this describes a wavelength of 26,000 years. It's not always 26,000 years, of course. It varies a little bit, plus or minus 500 years or so. But it's a predictable, roughly average 26,000 year cycle. And we can use that in dating our megaliths, but we can also use it in paleoclimatology. As I've spoken about before on this channel, I also wrote a science paper on the modulation of ice ages, and of course we use this precessional data in that dating. This was called modulation of ice ages via precession and dust albedo feedbacks. It's been very successful, actually, very controversial, because it says that CO2 was not the primary feedback agent that was controlling ice ages. It was dust and ice sheet albedo, the reflectivity of the ice sheets. So do have a look at this. There is a talk here on this site about the modulation of ice ages. So that's one way we can use precession, but we can also use it for dating our megaliths. And here is one method we can do this via the layout of the pyramids. So what are we looking at here? Well, you can probably recognize this, but let's put some dates some names onto these little structures here. Here at the top we have the Giza pyramids, and then we have the Red Pyramid and the Bent Pyramid. And there's an angle there of about 55 degrees between the two. What is this layout demonstrating? Well, the angle I'm really interested in is the one down here. Between the straight line and the bent pyramid, we get this angle of 191 degrees. And that happens to be 11 degrees displaced from a straight line. And that was interesting because the Great Pyramid is based on pi. Its design and layout is based on pi, which is 22/7. That's the approximation of pi that they used. And so we get lots of the number 22/7, which is pi, 11/7, half of pi, or 5.5/7, quarter of pi. And so the number of 11 is intimately linked to the Great Pyramid. So that was interesting. But where else can we see this layout? Well, one place we can is if you look on a planisphere, because this looks awfully like these stars and points. So what are we looking at here? Well, As you probably know, the top one here is Orion, because it's long been said that the Giza pyramids look like the belt of Orion. And the points down the bottom, as you can see now, are the ecliptic pole and the celestial pole, the two poles that we were looking at just a minute ago with the precession of the equinox. And we even get the same sort of angle here at the top. Between the Giza pyramids and the actual planisphere, we get a very, very similar angle. And so we get this very similar layout between the pyramids and what we will see on a planisphere. As above, so below, copying the layout of the stars and the heavens onto the surface of the Earth. And as we know, this celestial pole down the bottom here rotates around the ecliptic. It forms that big yellow circle in the heavens above, and that is the ecliptic circle as the celestial pole rotates around and around. And that's interesting because on an electronic, a computer planisphere, we can change this angle here bit by bit, decade by decade, until it equals the same as we see on the ground at Giza and Dashur. And if we do so, we get a date, and a very accurate date too, down to about 5 or 10 years. And that date, we're going to arrange this angle so it equals the same as we see on the ground at Giza and Dashur, and we get a date, and that date is 13,500 years ago. Very much the same as we've already looked at. So if this is what the designer of the Giza pyramids and the Dashur pyramids was thinking about, if this was one grand plan, as above, so below, mimicking the layout of the heavens above, then we can say that Giza and Dashur were built, the design date for these structures was 13,540 years ago. Much older than is given credit for. Can we confirm this at all? Well, quite possibly, because you're probably familiar with this layout. Here is the Sphinx looking at Leo, and you've probably heard that you can do a precessional dating by the Sphinx looking at Leo, because the constellations change every thousands of years due to the precession of the equinox. So it not only makes the celestial pole spin, it also changes the constellation that rises at the vernal equinox, the spring equinox. That is why Leo is looking east, looking at the constellations coming up over the horizon. It is precession watching. That is what the Sphinx is doing. And we get that date you've probably heard about, 10,500 BC, or about 12,500 years ago. But of course, it's not exactly that, because Leo is quite a big constellation, and so we get an exit from Leo of about 10,000 years ago, and an entrance to Leo of about 12,500 years ago. That's the date that everybody knows about, when we're entering the constellation of Leo at the vernal equinox. What I'm taking here is actually the median between the two, so the center point, which is about 11,250 years ago. And this is not the same as we've just calculated from the layout of Giza and Dashur. We're over 2,000 years different. So they don't agree. But is that what Leo is that what the Sphinx is actually doing? Because if we look at the layout of Giza, here's a nice satellite photo of Giza. And what they're saying is that we're looking due east at the vernal equinox, the spring equinox, for the constellation that is rising. And here is the Sphinx looking very small in comparison with the entire site, looking east at the rising constellation. But is that what this design is actually showing? Because the Sphinx is actually on the second pyramid causeway, and that does not point east. It has a very specific alignment. It's aligned at 14 degrees from the due east. And that is a very specific point. It's known as a cross quarter. It is actually 1 month displaced from the spring equinox. So in this case it will be February the 19th or 20th instead of March the 21st. It is a very specific angle and a very specific date. So what it seems to be saying to me is that here is the Sphinx looking due east on February the 19th, not at the vernal equinox, the spring equinox, at the cross quarter, February the 19th. And of course that will change the date. And so we get two sets of dates now. We get this date, which is the cross quarter date, which is 13,500 years ago. And of course, from the layout we did of Giza and Dashur, we got 13,500 years ago. So we have a confirmation from two different methods of looking at precession within the Giza plateau. We get the same date. So is that confirmation or is that coincidence? I rather think that's probably confirmation. We've seen that these pyramids look older than they are currently given credit for. And here we have two methods that come out with the same date, 13,500 years ago, which is interesting. But how can we confirm this? We like confirmation. We like as many confirmations as we possibly can. Well, these are not the only megalithic monuments. We also have other megalithic monuments that might be aligned to particular astronomical events. And here's one of those. Ah, yes. We're back at Stonehenge. Stonehenge and Avebury, megalithic monuments that might be of the same era, same megalithic era as Giza and Dashur. And it's possible that we might get some astronomical dating from these monuments as well. And of course, I'm not the first person to look at this. We go all the way back here to Flinders Petrie in 1880 and his plans, descriptions and theories of Stonehenge. And he looked at the precessional dating of Stonehenge. The only problem was he got his precession back to front, and so he thought Stonehenge was built in about 600 AD, which is why you had all of these ideas that Stonehenge was post-Roman. It was because of Flinders Petrie getting his precession back to front. Anyway, precessional dating goes back to the 19th century. And here's someone else who did the same. This is Norman Lockyer in 1900, and he did a full survey, a very professional modern survey of Stonehenge, which was good. And he did a precessional dating, and he pointed out that Flinders Petrie was back to front. And Lockyer came out with a date that was more like 1600 BC or something of that nature. And then we had Richard Atkinson, 1950s, and he did a bit of precession, a little bit, but I was somewhat disappointed with this. He did a full survey of Stonehenge, which is good. But he then said, we don't really have to do much of this precessional dating because we now have carbon-14 dating. which I was a little bit surprised at. I would have thought that don't you want to confirm your carbon-14 dating by having a look at some precessional dating as well? Anyway, he rather disregarded the precessional side of it in favour of carbon-14. Then we had Gerald Hawkins, 1960s, and he was a professor, astronomer, and he did a very good look at the movements of the heavens around Stonehenge, trying to date it via the movements of the moon and the sun, and having all of these alignments. And it was a very interesting book, but he was rather going on, he didn't resurvey Stonehenge, so he was going on old surveys, and he was using survey documents, and so his measurements were not entirely accurate. He estimates not more than 0.2 of a degree of accuracy, and some of these maps and charts of Stonehenge have actually changed over the years, so the surveys were not entirely accurate. Anyway, it's a very interesting book. Do read it. It's got a lot of information there. But he doesn't use precessional dating that much. Same goes for Fred Hoyle, another astronomer, who did a very interesting book on Stonehenge, looking at astronomical alignments. And again, he didn't do too much in the way of precessional dating. But it was nice that well-known professors would actually look at this side of Stonehenge and Avebury, because modern academia tends to not do so. It looks down on such things as astronomical alignments, as if ancient man was not capable of aligning a monument with a particular celestial event. And then, of course, we had Alexander Thom, who did a lot of survey work and a lot of celestial dating of these monuments. And again, a very interesting book. And he invented the megalithic yard, of course. He discovered the megalithic yard. But in this part of this talk, I want to look beyond Thom and Petrie and Lockyer and look at all of the possibilities, because there are many possibilities that they did not explore, and I want to explore those possibilities. So here we're going to look at obliquity, because I think this is encoded within these particular monuments. So what is obliquity? It is the tilt angle of the Earth, which changes, maybe surprisingly if you don't know this, but it changes from a minimum of 22.1 degrees up to a maximum of 24.4 degrees. So the tilt angle of the axis of the Earth changes by over 2 degrees. And we call that the obliquity angle. You will hear me talking about obliquity. And we might be able to use that to date our monuments. So what monuments may encode obliquity? Well, one of them might be Avebury. So this is the layout of Avebury. A huge circle on the plains of Wiltshire with entrance gates in the sort of north and south and east and west, and those two smaller circles in between. And it's so big, it's about 450 meters, I think, across, that it's got a village inside. And the very center of Avebury is, of course, a pub. The Red Lion, right in the very center of Avebury. So perhaps we can speculate that the most important artifact was built first. That was the Red Lion, and then they built Avebury around the pub. Well, possibly, but what else was Avebury designed to represent? I mean, there's an awful lot of work gone into this construction. What did it represent to ancient man? What is a circle inclined slightly from the due north, floating in space as it were? What is that circle? I think it is an image of the Earth. And of course the Earth has an axis exactly the same as Avebury has an axis, around 22.5 degrees. Possibly. We'll look at that in a minute. And Avebury has an equator, the same as the Earth has an equator. It looks to me as if Avebury is an image of the Earth floating in space, which is interesting because it means that ancient man must have known the form and shape of the Earth and its angle of inclination, its obliquity angle. And of course that angle that is drawn here is well within the limits of the Earth's obliquity. We saw it went from about 22 degrees up to 24.5 degrees. So this angle is well within the limits of the Earth's angle, tilt angle of its axis. And there are other reasons for me thinking this, because these small circles that are in Avebury here, these contain latitudes of specific objects on the surface of the Earth. I won't go into that. You'll have to read the books for that. But these latitude angle, these lines of latitude for these specific objects in these two circles indicate that whoever designed Avebury knew the division of the Earth into lines of latitude. You see them here on the Earth picture. And knew how to calculate where objects were on the surface of the Earth with their specific latitudes. That is another reason why I think that Avebury is an image of the Earth. And so where do we get this data from? Well, we get it from Lascar again, Monsieur Lascar over in Paris. And just like Precession, he's calculated obliquity, the tilt angle of the Earth, going back 20 million years. So again, this is a very, very stable and predictable cycle that the Earth goes through. And from that data, we can it's freely available. You can download that data and you can draw a nice little graph. So what are we looking at here? Well, down the bottom, we have dates from 0, today's date, going back 100,000 years. And on the left, we have the angle of obliquity, the tilt angle, all the way from 22 degrees up to 24.5 degrees, let's say. And it draws this nice little sine wave. And the sine wave is not constant, of course. The amplitude changes. It's not always down to 22.1, I think, was the minimum. It does change, as you can see on this graph. And we can check that this data is correct, because this is my own graph. I've plotted this graph. We can check is correct by looking at today's data. Well, before that, we'll have a look at the amplitude. So, not the amplitude, the wavelength. So this sine wave, this cycle, is a 40,000 year cycle. So precession comes in at 26,000 years, and here we have obliquity at 40,000 years. Again, it changes. It's plus or minus 1,000 years, but it's very predictable in the way it moves. It's a 40,000 year ticking of the clock, or a metronome, ticking away like a very accurate clock. And just as we can use a clock to determine a date, we can use this obliquity clock to determine the age of our megalithic monument. And as I've just said, we can check that this graph is correct by looking at today's date and today's data. Here is modern obliquity at 23.4 degrees, and all we need to do is run along this sine wave until we reach here, drop a perpendicular, and it comes to today's date, 0. And so the data I've plotted here is correct. 23.4 degrees gives a date of 0, today's date. But of course the date given by Avebury was not 23.4 degrees. It was indicating a tilt angle for the Earth of 22.5 degrees, almost a degree different. So where would that be? Well, it would be down here. Here's the Avebury obliquity, 22.5 degrees. And from that we can get a date, because all we need to do is intersect this light blue sine wave and drop a perpendicular. And here it goes. Here's the perpendicular, and we come out with a date. And here is the date up the top here, 24,000 years ago. A very long time indeed. And remember, that's the first intersection with this obliquity sine wave going back into the past. Here's today's date. Here's today's date. And this is the movement of the tilt axis of the Earth. And this is the first time we intersect 22.5 degrees. It was 24,000 years ago. So if that is what the designer of Stonehenge was actually depicting on the layout of Avebury, that it really was indicating the tilt angle of the Earth, then that design is indicating a date 24,000 years ago. That is probably the construction date for Avebury. A very long time ago indeed. But if we want to be brave, that's not the only date it was indicating, because this sine wave continues on back into the past. And so we can get other dates. We can go back to this point here, which is 33,500 years ago. Or this one, all the way back to 66,000 years ago. Or perhaps, if you really want to go out on a limb, this one at 74,000 years ago. It's your choice. At each of these locations, the tilt axis of the Earth was 22.5 degrees, the same as is indicated by the layout of Avebury. And we have no real way of discerning at this point in time which one of these is correct. It could be 24,000 or 33,500 or even 66. It's rather up to you. How old do you think Avebury could possibly be? Well, can we make a confirmation at all? Well, possibly, because we have another megalithic monument just up the road, which also might be pointing at some sort of celestial alignment. And that is this temple, Stonehenge. And again, we might be able to get a date out of this. So this is a classic image of Stonehenge, looking at the megalithic henge made of stone. But what we actually want to look at is from above. So here's Stonehenge from above, and you see that we not only have the well-known stone element in the center of the circle, we have a henge around the outside, an earthen henge. And that's what we want to look at. So we're looking at this, the earthen henge around the outside. And then we also want to look at these two smaller earthworks to the north and south. These ones. Those, I think, are the most important. For this bit of the investigation, the Stonehenge is a bit of a distraction, a bit of a glistening bauble in the centre of the henge, when actually what we're looking at is going to be the earthen henge. And I think it has something to do with precession again. So here's our image of the Earth precessing, the same as it did before, and it draws this big yellow circle in the heavens above. So if you go out on a winter's night and have a look at the heavens above you, you'll see this big yellow circle in the heavens above, and that's the ecliptic circle. The Earth, the axis of the Earth, draws a circle in the heavens above, the ecliptic circle. And here is Stonehenge, and it's drawing circles to the north and south of the Stonehenge in the centre. So we could replace perhaps that Stonehenge with an image of the Earth. And then we have those two little circles to the north and south. And what are they representing? Well, I think the answer is obvious. They are representing the ecliptic circle, that big yellow circle in the heavens above, or the heavens below if you happen to be in the southern hemisphere. And that is what is being drawn on the image of Stonehenge. And again, this is interesting. Like at Avebury, it would appear that the designer understood the movement of the Earth, the precession of the equinox, the movement of the celestial pole as it moves around the ecliptic pole. And this is interesting because it's not only demonstrating a knowledge of precession, the size of these circles to the north and south, they grow and they shrink with the angle of obliquity, the tilt angle of the Earth. So if you can calculate the size of these circles, then you can calculate the obliquity angle, just as we did at Avebury, and therefore possibly come out with a date. And we can do this at Stonehenge. So let's look at Stonehenge actually precessing. So this is the Earth precessing on its axis and drawing those big yellow circles in the heavens above. And that's why we have these circles at Stonehenge to the north and south of the Stonehenge site. These are the precessional circles. And as I say, you can actually maybe calculate the size of these circles, which may be able to give us a date. So here is a layout of Stonehenge. And as we did before, so we've got the celestial axis running up here and the ecliptic axis here. And so we can maybe drop in an image of the Earth in the center. And we have our two small circles to the north and the south, which are our ecliptic circles created by the precession of the Earth's axis. But how big are these circles? Well, they actually go between the celestial axis and the ecliptic axis. And I think that the designer of Stonehenge has left a calculator to exactly calculate how big these circles should be. And we know these as being the Aubrey holes. And there are 56 holes around the perimeter of Stonehenge. You can see them here, all around the perimeter. And nobody really knows what these stones are. Some have said they are post holes. Some have said that they hold the blue stones before the blue stones were moved. Others have said that these stone holes have always been empty. But empty or not, once they've been dug into the chalklands of Stonehenge, they will leave their mark, and any survey will pick up these holes, which is exactly what happened. They were discovered very, very quickly by Mr. Aubrey, hence they are called the Aubrey holes. And so there are 56 of these holes within 360 degrees, and so each hole is displaced from its neighbour by 6.43 degrees. And this might not look like a very inspiring number, but if we calculate how many holes there are between the celestial axis and the ecliptic axis, we get 1, 2, 3, 3.5 Aubrey holes. And 3.5 Aubrey holes times 6.43 is 22.5 degrees. The same as we found for Avebury. Which is interesting because from that we can get a date. And so the Stonehenge obliquity is the same as the Avebury obliquity, is 22.5 degrees. And we can confirm this by a nice little triangle that is centered in the middle of Stonehenge. So if you look on the left here, we get this red triangle, and it's a very specific triangle because it's a 5, 12, 13 Pythagorean triangle. And these, as you know, are very special triangles because the side lengths here end up as whole numbers. And there are not very many of these special triangles, only a certain few. And so for someone to have put this special triangle here in the middle of Stonehenge means they understood the Pythagorean theorem. They were consummate mathematicians back in this era, whoever made and designed Stonehenge. And the interesting thing is that this Pythagorean triangle has an angle here of 22.6 degrees. So we have Stonehenge obliquity was calculated from the size of the precessional, the yellow precessional circles, was 22.5 degrees. And from this triangle, this Pythagorean triangle, we get 22.6 degrees, and that is the closest we can possibly get with a Pythagorean triangle to our favorite 22.5 degrees. This is a confirmation that this is the angle they are looking for, the designer of this site, that the yellow circle, that ecliptic circle in the heavens above, is 22.5 degrees wide, which means the obliquity angle, the tilt angle of the Earth that we think was present when Stonehenge was made, was 22.5 degrees. And it's exactly the same as the Avebury obliquity, as I've said. So they are all looking at this special angle of obliquity for some reason. Presumably because that is the angle of obliquity when these monuments were constructed. And so we can go back to our graph. This is the same graph we saw before. So we have dates along the bottom, 0 here, 100,000 years ago here, and degrees of tilt angle along the left here. And so we can draw in all of those points that we saw before. But this time this is the Stonehenge and Avebury obliquity, because they are both exactly the same. And from that we get these dates that we've seen previously. So what we're saying is the youngest we can get for Stonehenge and Avebury is 24,000 years ago. And if you're very brave and you want to go back further, you can go back to 33,000 years or 66,000 years or even 74,000 years ago. That is what the design of these monuments is telling us. So why don't we believe it? Just because we've been told these monuments are only 4,500 years old, based on very little data, based on carbon-14 dating, that may not be associated with these sites whatsoever. So can we confirm this? Well, one way we could confirm it is by looking at maybe another site, maybe like the Giza site that we looked at before. So let's put on the Giza date. And if you remember, the Giza date was 13,500 years ago. And that is indicated here by this pink arrow here, pointing at 13,500 years ago. And it doesn't match, which is a shame. It would have been nice to have the same sort of date. But we don't. We have a different date. But of course, the Giza date is a precessional date. And we don't have to go for the first precessional cycle in the past. We can go back to previous precessional cycles. Now remember, the precessional cycle is about 26,000 years long. So let's draw on those other precessional cycles. And if we do so, we get 39,000 years ago, 66,000 years ago, and 91,000 years ago. And we do get a match, but only right back here at 66,000 years ago. A very long time indeed. Is that possible, you may ask? Well, let's have a look at this graphically, because it's probably easier to see. So let's draw a little graph of these dates. This is our megalithic construction date chart. And on the left side here, we get thousands of years ago for the construction date of the megaliths, between 0 and 100,000 years ago. And at the bottom here, we have the four methods we've just looked at for dating these megaliths. We have the Sphinx cross-quarter date. That's the Sphinx looking at the rising of Leo. We have the Giza layout date, where we have that image looking above at Giza and Dashur. We have the Avebury obliquity, where we have Avebury as an image of the Earth tilted over at 22.5 degrees. And we get Stonehenge obliquity here, where we get those precessional circles to the north and south of Stonehenge, which are 22.5 degrees wide, indicating an angle of obliquity of 22.5 degrees. So let's draw on points for our dates. So let's look at the youngest ones first. So here's all the youngest dates. We get the Giza dates at about 13,000 years ago, and Avebury going back 24,000 years ago, Avebury and Stonehenge. And then we can look at the older dates, going back here at Giza up to 40,000 years, and even older dates, and even older, if you really want to go out on a limb, even older dates. And these are all the dates we've managed to deduce from these celestial alignments and images. And so, well, what are we going to choose? The youngest, and perhaps the most obvious of dates, are these ones. So here we have Avebury and Stonehenge at 24,000 years ago. Again, a very long time ago indeed. But then we have this 10,000 year hiatus where nothing was happening before the Giza site was built, which you might say explains why Giza and Dashur are more technical than Avebury and Stonehenge. I don't know, that could be an argument. But we get this 10,000 year gap between these two megalithic sites. Is that reasonable? Well, I don't know, but if you would prefer that this was one megalithic era, that all of these monuments were built all around the world, were built at the same time, including the ones in Central America, of course, and any of the ones out in Asia. If they were all built at the same time, then you rather have to look at this date, which is 66,000 years ago. Is it possible that these megaliths could have lasted that amount of time? Well, certainly at Giza and Dashur we have a little bit of a problem, because how long will a pyramid last? Well, these pyramids were actually built using Tura limestone casing blocks, which are very durable, very tough. They don't weather very easily, as we've seen. So could Giza and Dashur have lasted in the fairly benign sort of environment of Egypt, although the weather did change in Egypt over the millennia. It has been wetter in Egypt than it is now. Could these pyramids have lasted not just 13,000 years, which they certainly could have done, but 66,000 years? Could they have lasted that long? It's possible, but we have nothing to compare these erosion patterns at Giza with. So we can't really get a good estimate of how long it would take to erode away these casing blocks. And what about Stonehenge and Avebury? Well, certainly the megaliths there, they're made of very, very tough sarsen sandstone. And that would last, undoubtedly, 66,000 years, no problem. The problem at Stonehenge and Avebury is the earthworks, the ditch and the banks. Now, they would start to erode much more quickly, and they would get covered up fairly soon. Well, I say soon, within maybe 10, 15,000 years. But you could postulate that someone was there digging out the ditches and remaking the banks every century or so, keeping the site in pristine condition, and in that fashion the ditch and banks could have lasted an awful long time, as long as people had always been there to maintain and repair the site. So it is possible that they could have lasted that long. It's stretching things a little bit, I would say. I would prefer the younger dates. I would prefer a date around 13,500 myself, but the earliest dates we get for Stonehenge and Avebury is 24,000 years ago. That's still a long, long time. And the other thing we have to think about is ice ages. Stonehenge and Avebury being in the north, could they have lasted through the last ice age maximum, which was circa 15 or 17,000 years ago, when the ice sheets started to melt? Could they have lasted through the glacial maximum? Well, here is the glacial maximum, and this is the maximum extent of the ice sheets across Britain. And we know exactly where these ice sheets ended, because they left their marks out on the topography of Britain. So they left drumlins underneath the ice sheets, terminal moraine, erratics as they're called, the stones that dropped off the edge of the ice sheets, and the big lakes in Cheshire where lumps of ice sat on the ground and made these great depressions in the land. So we're fairly confident we know exactly where the maximum extent of these ice sheets was. And this was the maximum extent. But of course, Stonehenge and Avebury are down here in Wiltshire. And so they would have been clear of the ice sheets. And so they would have lasted, or could have lasted, through the last ice age maximum. And they could, I suppose, have even got bluestones. This is the area from which bluestones were derived from. And even that is in the clear. So bluestones could have been brought from the Presili Mountains to the Stonehenge site in the Ice Age era, because they were clear of the ice. Furthermore, it would have been easier to transport because this this estuary here, the Severn Estuary, would not have been there during the Ice Age. That would have been dry land because the sea levels were 140 meters lower than they are today. So it would have been much easier to transport the stones from Presili over to Stonehenge during the Ice Age. But of course, any of the other megaliths that we know about, from Scotland and from Ireland, all of those megaliths must be younger than 11,000 years ago, because they would have been covered in ice during the last Ice Age. They would have been destroyed had they been built before the last Ice Age. So all of those megalithic monuments must be much younger. They must be post 11,000 years ago. But when you look at those megaliths, although they might be impressive, they are within the capabilities of man, we might say. They are smaller than Avebury and Stonehenge. The stones are smaller. The actual henge, the ditch and bank, is smaller as well. They are conceivably constructed very easily with normal techniques, without having to look at anything esoteric. And that would be understandable, because everybody wanted to repeat what they saw down at Stonehenge and Avebury. It's like the major church building era in the Middle Ages. People saw the local massive cathedral, like at Salisbury, for instance, one of the largest in Europe, with the largest and tallest spire. And they would have been inspired, no less, from looking at these great cathedrals, and they would want a cathedral in their smaller town and village. And that's exactly what they did. They went back to their towns and their villages, and they built smaller cathedrals. We call them churches or chapels, and everybody built one in their town or village. Well, they would have done exactly the same during the Neolithic era. They would have come to Stonehenge and Avebury, seen these massive cathedrals, and gone back to wherever they lived, and they built a smaller henge in their local village. And that is why I think we have this great proliferation of these megalithic sites across Britain. And they would all have been younger than the last Ice Age. And what would conditions have been like? Okay, Avebury and Stonehenge could have survived the last Ice Age, but what would conditions have been like if you were building or maybe visiting this site? Well, certainly this would be a summer project only, because this would be like being up in the tundra now of Canada or Russia, in the far north of Russia today, where the conditions during the winter would have been inhospitable. You would not be able to live in this region here of Stonehenge during the winter. However, during the summer, the tundra can become quite balmy. It's warm. It has 24-hour, well, it wouldn't have had 24-hour here, but up in the far north now, it has 24-hour sunshine. At Stonehenge, it would have the same amount of sun as we have now. During the summer, we get not 12 hours, but maybe 16 hours of sunshine each day. It would have been warm. It would have been balmy. Animal life, plant life, all growing in this area. Because, and this is one of the little secrets of paleoclimatology, when we look at the ice ages, everyone thinks it was freezing cold during the ice ages. Well, perhaps, but during the summer, the sun was actually stronger than it is now. And if you don't believe that, let's have a look at a graph. Here is a graph of insolation, we call it. So on the right-hand side, insolation. That's the strength of the sunlight coming from the sun, hitting the ground at 65 degrees north, so just a little bit further north than Stonehenge and Avebury. And that is the blue line here. That is the sun strength going back over 100,000 years. So at the bottom here, we have 50,000 years ago, 100,000 years ago. And here on the right, we have the sun strength at that latitude, and it goes all the way from 420 watts per square meter up to 540 watts per square meter. So there is a great change here in the strength of the sun, going all the way from, well, say from here at 460 up to 530. Changing by 70 watts per square meter. That's more than 20% change in the strength of the sun over the millennia. And if we drop down today's date, as it were, year zero, here it is on this purple dotted line. Here is the current sun strength at these northern latitudes, 480 watts per square meter. And as you can see, for most of the last 100,000 years, the sun strength during the Ice Age has actually been stronger than it is now. So the red line here is temperature, and you can see temperatures were going down and down and down all the way to about 17,000 years ago. So it was getting colder in the north, but the sun strength was actually warmer than it is now. And that's one of the big conundrums of paleoclimatology and the ice ages, where many scientists didn't understand why you can get very, very strong sun strength in the northern hemisphere and no temperature increase. All along here, the temperatures were higher, sorry, not the temperatures, the sun strength was higher than it is today, which is the dotted line here. And yet the temperatures of the northern and southern hemispheres continued to cool. Why did it do so? It was because of albedo, the reflectiveness of the ice, which was rejecting all of that insolation, all of that sun strength. And so the climate continued to cool. But during the summer, if you were up there at Stonehenge and Avebury, the sun strength would have been warmer than it is now. So summers up against the ice sheet would have been quite balmy. You could indeed have made an expedition, a pilgrimage, you might say, coming up from southern France or from Spain, where it was warmer, of course, and quite a good environment to live. And you could have made your pilgrimage up to Stonehenge and Avebury during the summer months. It would have only taken you a month to walk up there. You can actually walk quite a long way in 1 month. That's how people travelled back in the era. You could have made your pilgrimage to Avebury and Stonehenge and gone back again to your house as your lifetime's Hajj, you might say, the visit you have to do once in a lifetime to go and visit Stonehenge and Avebury, and then gone back to southern France or to Spain. So it is entirely possible that these were recognized and used temples in that era. Might be stretching the bounds of possibility, but it is possible. I would prefer myself the younger period, maybe 20,000 years ago. 66 sounds an awful long time ago to me. I'm not sure that Stonehenge and Avebury could have lasted that long. But there you go. The choice is yours. So what is the conclusion? Looking at the celestial alignments and designs and depictions of these particular megalithic monuments, what can we say about them, about their construction date? Well, it's telling us that the megalithic era is 13,500 years ago for Giza, or 24,000 years ago for Avebury and Stonehenge, or if you want them built as one megalithic project, you have to go back about 66,000 years ago to have them both with the same astronomical alignments and depictions. A very long time ago indeed. So that's food for thought. Perhaps the megalithic era, perhaps these megalithic monuments are much older than you think.